Testing for aldehydes and ketones. Since both aldehydes and ketones are the same carbonyl group, and most of their compounds tend to have the same odor, specifically the ones that are with the shorter chain length. So, testing for them and differentiating between them is an important part of the process. And that's why we usually go with this. This does not just belong to organic chemistry, this also belongs to analytical chemistry as a part of analytical tests. Since you remember doing some analytical tests back in IGCSE, if I be specific, I would say the test for cations and the test for anions and the test for some important gases. So here we are with this for some important homologous series in organic chemistry. So these tests are important, and these are important for all three papers. Apart from what we are about to study in what's going to happen in background chemistry and how we're going to condense these two molecules into one, producing our main product along with that a simple small stable molecule such as water. We are also going to study upon what happens in terms of observational chemistry, what happens, what kind of color changes you have, or do you have any precipitate formation or not? So, as always, like the chemistry has two sides, the background chemistry and the foreground observational chemistry, we're going to do the same thing in here. Let's start for testing with the carbonyl group. This is to differentiate the carbonyl group from other group, remember, and I'm going to specifically emphasize upon this by drawing. This is carbonyl group. Now, if I simply put an H over here, it is a subtype of carbonyl group that is aldehyde. If I put an O over here, this is the specific type, not just the type, this is the specific homologacies of carboxylic acid. If I simply erase this H, this becomes the ester group. So it's the same carbonyl group to which we are actually giving it a small bit of a change, and it either converts into a subtype or converts into a complete another homologous series. So that's important that we identify this carbonyl group and do not mix it with any other homologous series. So testing for carbonyl group, that means it would be either an aldehyde or a ketone. What do we use? We commonly call it 2,4-DNPH as the abbreviation, which is also written over here. By the way, it's dinitrophenylhydrazine. Now, let me clarify. Di means two. Nitro is actually for NO2 group in organic chemistry. Phenyl is the benzene ring, which then have one higher place available for a bond. And hydrazine actually goes for into H4, basically, which is a single bond between two NH2 groups. All right. This is what we commonly call hydrazine. This whole formula comes out to be like this. Now, those two NH2 groups can then combine with the benzene group, and then there are another two nitro groups on there. So take a look. One NO2, second NO2, this entire NH2 in which one hydrogen is taken out, one hydrogen is also taken from here so that they both can combine, hence 2,4-dinitrophenylhydrazine. Now, uh, I am also going to make sure that you understand a little bit of naming over here, though this is mostly going to help you with A2 chemistry, but that it's important if you learn it over here since it's going to help you with AS as well, a little bit though. But this is the main group. Now, since this is the green group, this position will be taken as 1. Now, the nearest numbering will be for this group, the NO2 group, so give it as 2, and then this corner is 3, then 4, then 5, then 6. So that's how 2, 4 for our subgroups, and 1 for our main group, hence 2, 4-dinitro, and then phenylhydrazine. That's how it's named. Okay. But apart from all the nomenclature moving ahead, it's actually a condensation reaction. Remember, in a condensation reaction, two separate molecules or two molecules with different homologous series tend to meet together, form a bigger polymer or molecule or a bigger molecule than either one of them, and then they also eliminate a simple, small, stable molecule. It can be water, it can be HCl. You have came across those two examples in IGCSE. Then it can be also methane or ammonia. So we mostly deal with water, and you have seen most examples of water previously in IGCSE. So it's going to be the simpler one as well. This is also going to be this 2,4-dinitrophenyl hydrazine. And then we have taken an example of an aldehyde over here, as you can see. Now, this can be an aldehyde, this can be a ketone, but whatever that is, the good part is that we always will have the carbonyl group. And the carbonyl group will have the oxygen that can combine with the NH2 of the hydrogen to form water. And this carbon doubly bonded nitrogen will then combine to form an entire molecule. And instead of hydrazine, this would now be converted into hydrazone. All right. We would instead call it 2,4-dinitrophenyl hydrazone. This is the naming that we don't specifically teach at this level, but we ask the students to remember it just for the sake of AS. And when you go to A2, we explain this nomenclature in detail, but to understand a few bits of it, I've already explained those smaller parts. Okay, so let's move on. It's clearly a condensation reaction, giving us a bigger molecule, and then a small, simple, small, stable molecule along with it. So other classes of organic compounds that also contain the carbonyl group, such as carboxylic acids and esters, do not form the precipitates. So now this clearly separated the carbonyl group participants or the other counterparts, as which I previously explained, they do not form the precipitates, which means this one is going to be a precipitate. This one won't dissolve in water. Now, clearly, it was dissolving in water because of the hydrogen bonding, but now the hydrogen bonding becoming less and less. That's why. Okay, so now we have a practical activity to explain the same thing, 2,4-D and pH testing with, this time we probably will use, what are we using over here? An aldehyde or ketone. They haven't specified anything. Now, if a aldehyde or ketone is present, a deep orange precipitate would form. If not, no precipitations would form. Now, the precipitate form can be purified by recrystallization. Its melting point can be measured experimentally. The identity of the precipitated compound can then be found by referring to the melting point data, and this would give us the idea which aldehyde or ketone was it. So these three lines may not seem significant, but they really are because we have many past paper questions from it. Now, this is going to be a really beautiful deep orange precipitate we're going to get after this experiment. The experiment is pretty easy. As shown, it is usually done in a test tube. So very little amount, hardly 1 to 2 cubic centimeter or 3 cubic centimeter of our compound is enough to perform this test and get the idea whether it's an aldehyde or ketone or some other carbonyl group-based compounds. So now, since we know and we had a precipitate, a deep orange precipitate, we know it's carbonyl group, so we need to distinguish between aldehydes and ketones. Now, what your book is going to do is that we are going to perform the tests that are considered important tests. So, unfortunately, those tests are most commonly detecting aldehydes and not ketones, but you have to go with this. The absence of aldehydes would automatically mean that it would be a ketone. The point I'm trying to make is that go for this deep orange precipitate. If you get it as a positive test, you get a precipitate, go for these tests. The first one is with tolerance reagent, which actually tells us whether it's an aldehyde or not. If the test is positive, it's an aldehyde. If you had a deep orange precipitate before, but you didn't get this precipitate as per this test is positive with tolerance reagent, you don't get this silver mirror that we usually call it. That means it isn't an aldehyde. Automatically, it would be a ketone. Why? Because the carbonyl group was confirmed. So if it isn't an aldehyde, it must be a ketone. That's how we go with it. There is, however, another test, a Pelling solution test. Unfortunately, this test also gives us a different color if we have an aldehyde. So if this test gives you a different color before and after, blue to red, usually you have an aldehyde with you. If this doesn't happen, it stays blue. It's definitely not an aldehyde. But if previously you have got a deep orange precipitate and it's not an aldehyde, it's definitely a ketone. That's how we go with this. Now, you might have an idea if we have so many beautiful tests for aldehydes, why don't we have some good tests for ketones? Yes, we do in chemistry, but that's not a part of your book. So let's stick to what we have in the book. All right. Now, testing with tolerance reagents. These are all the names of the scientists upon which we have named the reagents. Tolerance reagents is actually an aqueous solution of silver nitrate in excess ammonia solution. Silver nitrate, AgNO3, excess ammonia. Sometimes it's also known as ammoniacal silver nitrate. Now, it's also spelled as ammonia, ammoniacal or ammoniacal. You can put this A or can take it out of the pronunciation. It entirely depends upon you. Now, the silver ions, Ag positive, in the solution act as a mild oxidizing agent. When warmed, these ions are going to oxidize the aldehyde to form a carboxylate ion. Under the alkaline conditions, any carboxylic acid form is neutralized to its carboxylate ions. H positive is taken out, it would convert into a salt. So the redox reaction with an Ag positive ions would reduce the silver atoms, and those silver atoms are going to form an entirely good uh, silver mirror. This is what we call a usually silver mirror test. Apart from Tolan reagent test, we call it a silver mirror test because you are literally going to deposit pure silver in the form of a layer over here. So much so, if held properly, you would see a little bit of your image in it. That's why we call it a silver mirror test, right? So the silver mirror test actually takes those Ag positive ions, convert them into pure Ag, the Ag deposited, then forms a mirror inside of the test tube. This is a positive test for an aldehyde. If there is a ketone that is bound with tolerance reagent, no redox reaction would take place, and a colorless mixture would stay as a colorless mixture with somewhat of an ammonia smell with it, right? So moving on to the next practical activity, 18.5, we are going to test it with Felling solution. Now, Felling solution is an alkaline solution containing copper-2 ions. When warmed with an aldehyde, Cu2 ions act as oxidizing agent and they oxidize the aldehyde into carboxylate ions. But at the same time, what's going to happen is that they will get converted into copper-1 oxide. Now, this is the first time you're facing something like this. You have mostly seen copper in this form. And of course, if we are taking it with an oxide, the resulting formula would be CuO. This is the first time you're experiencing copper with a +1 charge. And of course, if we're going to form an oxide out of it, it would be Cu2O. Now, the Cu2O is actually an opaque red or orange color precipitate, which you can see over here, right? That happens after the complete redox reaction. And the clear blue Felling solution, it turns into an opaque red or orange color. Both colors can be mentioned. Both colors get you complete mark in it. Only aldehydes are capable of doing so. Ketones are not going to give this test to you. The ketones will stay blue, which gives us the idea that if the color does not change, it's not an aldehyde, it's a ketone. Now, though they are saying that this is the Felling solution, but quick fact for paper 3. Now, in the lab, you will have Felling solution as 1 and Felling solution 2, or usually we call it Felling solution A and Felling solution B in lab. Actually, Felling solution is present in the form of two different solutions in the lab. You need to mix them to prepare fresh Felling solution at the spot when you're about to use it. Because if we don't prepare Felling solution freshly at that spot, it usually does not give us the precipitate, right? So there would be two separate Felling solutions in the lab. You are going to mix them as per your need, a little bit of A, a little bit of B, usually equal amounts are taken, and then you prepare freshly prepared Felling solution. That would be then a mixture of these both would be the Felling solution you need to test against it, which would have a blue color and will in turn, in the presence of an aldehyde, would give you opaque red precipitate, right? But that was a quick fact just for paper 3, just for the lab purposes. You usually discuss with a single solution in terms of paper 1 and 2. Now, this completes our uh, testing methods, but one of the testing methods is taught separately. Why? It has a broader scope. Now, this testing method is for the formation of triiodomethane. As soon as you say the word, I hope you understand its methane is CH4. If that's triiodo, that means there are three iodine atoms, and of course they will come take its place in the form of substitution reaction. So we're only left with one hydrogen. So this is the methane now converted into triiodomethane. So the formula for triiodomethane would be CHI3, as the name suggests. Okay, we study this reaction separately. Why? Because this reaction has a very good scope. Your book is going to discuss a little less over here. I suggest if you have the book in front of you, keep the pencil ready. You're about to write a few things that are not written in the book, but that are definitely going to help you with answering the questions in past papers. Now, your book suggests that this triiodomethane or iodoform, which we usually call it, now remember, trichloromethane was chloroform, tribromomethane would be bromoform, and triiodomethane is commonly known as iodoform. Now it's a yellow precipitate. And this precipitate is usually formed with methyl ketone. Now, as soon as I say the word methyl ketone, it must give you the idea that ketone is a carbonyl group with carbon chain on both sides, but either one of them has to be a methyl, any one of them. It can be methyl on both sides, or it can be methyl on just one side. The another side can be as long of a carbon chain as you can think of, that's fine, but it would give a positive test and a yellow precipitate to form the iodomethane. Now, any compounds. So this test is good for ketones if the ketones are methyl ketones. All other ketones not going to give you this test. All right. So that's the first broader category that this test comes out positive with. Among all aldehydes, ethanol is the only aldehyde which consists of this group. You can think again, ethanol is actually formulated like this. So yeah, it has the CH3CO group. So among all aldehydes, again, that's why I was calling it a broader test. Ethanol would be able to give this test, turn this test as positive. Of course, the yellow precipitate would be formed at the end of the reaction. Okay, so they simply are talking about ketones and aldehydes, but we are going to take this test positive soon with alcohols as well. But first, the details that book discusses, and then I'll come back to it. Remember this COCH3 part and this COCH3 part, which we just proved for ketones and among aldehydes, ethanol. All right, we're going to prove the same thing for a few alcohols who are also going to give this test as positive. But the details in the book first. The reagent used is an alkaline solution of iodine, which are warmed together with the substance being tested. And at the end of it, we're going to get some yellow precipitate at the bottom. Now, the reaction involves two steps. The carbonyl compound is halogenated in the first step. The three hydrogen atoms in the methyl group are replaced by iodine atoms, substitution, of course. And we may call this substitution as halogenation. Don't forget, the substitution and halogenation were taught in one single reaction back in IGCSE. Now, the intermediate is hydrolyzed to form the yellow precipitates of triiodomethane, right? So, when separated from the reaction mixture, the yellow crystals of triiodomethane can be positively identified by their melting point of 119 degrees centigrade, something you need to memorize for AS papers. This is how we're going to uh, positively confirm that the reaction gave us the yellow precipitates were of triiodomethane, and their identity is confirmed by a physical property, melting point to be one of the best ones to follow, right? So the R in the alkyl group is actually uh, methyl ketone. It can be any chain. We have discussed it before. You see, you have the COCH3 part, you have the iodine, you have the alkaline medium, you warmed it with, and now it halogenated the CH3 part. But then this CI3 has to be separated in the form of triiodomethane during hydrolysis. So you are going to form a sodium carboxylate salt probably of the same R group, and you're going to form triiodomethane, which would be the yellow precipitates, which you separate uh, from the reaction mixture and check the melting point. So this is the reaction, but again, this can also be used for the testing of CH3CHOH group. Now, this is something very important. If I write it like this, CH3CHOH, and any part of the chain over here, I hope you understand this is a secondary alcohol. All right. So what we're going to do is that among the alcohols, the first one are secondary alcohols, which specifically have this formulation, CH3CHOH formulation. They are going to give this test positive. Apart from that, among primary alcohols, only ethanol is capable of giving this test positive. So yeah, this test really has a very broader scope, but this has some limitations as well. Yeah, now talking about the broader scope, it can confirm for us some ketones, some aldehydes, some alcohols, maybe primary, maybe secondary, but the limitations are they have to have this kind of arrangement for alcohols or a specific CH3CO arrangement for the carbonyl group. So there are some specific types of ketones or types of aldehydes or types of alcohols that we can determine with this test. So yeah, this test has a broader scope at the same time, some limitations to that scope. That's why this test has been given so separately, and they have discussed all the steps one after another. Now, you might think, why the ethanol? Then, in case the ethanol, this is the ethanol, and as soon as the oxidation occurs, this would be converted, and since we have discussed it before too, into this, right? Upon very first oxidation step, this would be converted into this. And this has the scope. Remember, aldehyde, ethanol can give this test positive. So yeah, since we have a setup of oxidation among there, so there is a possibility for ethanol to be first oxidized, then giving us the exact specific group for which the test comes out to be positive. This test can actually give this alcohol, although it's a primary alcohol, but can give the test positive, right? So the same thing has been explained over here. Secondary alcohol with the hydroxy group and the carbon next to methyl group. This would be first oxidized by alkaline iodide solution and iodine solution, and it would then give the RCOCH3, in which COCH3 is the part that usually gives the test positive, and we're gonna get the yellow triiodomethane precipitates out of it, and the sodium salt of carboxylic acid with it. So yeah, both with secondary alcohols of this arrangement or among primary alcohols, the ethanol have the capability to give this test positive. All right. So this was the broader aspect I was talking about. So triiodomethane has the capability of some really manipulative questions from Cambridge. Okay. Now, since this one is not that simple, so if you have any questions, throw them now. All right. Seems you don't have any questions, so let's move on. The last topic. Infrared spectroscopy. Now, before we move ahead, a little bit of some information that is going to help you with the last chapter of AS. and then you're going to face almost the similar things in the last chapter of A2. So a little bit of idea about the spectroscopy. Now, you have studied the spectrometry before, but spectroscopy is different. Now, when you use the word spectroscopy, definitely from spectro, the word spectrum comes into your mind. And yeah, we are clear about the light spectrum and how energetically this is divided into different spectrums of maybe IR or microwave or X rays or gamma rays or the UV rays. So, yeah, the spectrum is divided. Spectroscopy is a kind of study where we throw a specific light or a specific wavelength of light or a specific strata or substrata of the spectrum onto a substance and analyze it. Since the name is infrared spectroscopy, it automatically gives us the idea that it would be irradiated with electromagnetic waves in the infrared region of the electromagnetic spectrum, and then we are going to study our substance. Now, what's the point of doing this? Now, there are two kinds of tests. The analytical test that we keep talking about all the time, we have been just going with one type back in IGCSE and so far in AS. All our analytical tests have been chemical tests so far. We haven't talked about much about physical tests. We have been using chemicals. Now, using chemicals has a downside. We tend to use some transition elements or some poisonous chemicals and we test them. What do we do after? We dispose them down the drain and they become a part of us. And the earth balance for those ions is gets disturbed. And then we use the water from the same source. Of course, one day the water was supposed to get polluted, and now the water, the earth water, the groundwater is now polluted. So right now we are trying to come up with some green alternative for those chemical tests, and a great idea would be some physical tests. Now, physical tests, the good part about physical tests is that they don't require any chemicals. We don't dispose of any chemicals at the end of these tests. Infrared spectroscopy is one of those. In fact, any kind of spectroscopy would lie in the same portion because they're not going to use any chemicals, disposable chemicals at the end of the day. So the machine used is known as a spectrophotometer. It detects the intensity of wavelengths from infrared regions that passes through a sample. This analytical technique is particularly useful for organic chemists. Why? Because all organic molecules absorb radiation in the infrared regions of wavelengths. The energy absorbed corresponds to the changes in vibration of the bonds between atoms. Now, vibration is something that is usually important and then explains the idea of how the bonds can vibrate. Now, the bonds can vibrate by stretching, bending, or twisting. There are many videos on YouTube that can give you a very good idea about how they can stretch, or they can bend, or they can twist. Uh, in fact, even by just talking about it, it won't give you a good idea. So let's go through a YouTube video. Give me
To learn the types of molecular vibrations in infrared spectroscopy with the help of animation. We have two main different types of vibration. Out of that, one is stretching vibration and the other one is bending vibration. In stretching vibration, we have two types, that is symmetrical as well as anti-symmetrical. In symmetrical vibration, you can see here in animation that both the atoms are going away from the central atom and simultaneously they are going towards the central atom. It means that there is change in the bond length. Here, this is the second stretching vibration, that is anti-symmetrical. Here also you can see the little bit change. One atom is going away from the central atom and the other one is going towards the central atom, and the vice versa. When the other is going away from the central atom, at that time the first one will go towards the central atom. It means that again there is change in the bond length in these antisymmetrical vibrations. We have second major type, that is bending vibration. These bending vibrations are again four types. The first one is scissoring. Scissoring vibration is in a plane vibration. Here both the atoms are coming towards each other and simultaneously they are going away from each other, but both the atoms remains in a same plane. So that's why scissoring vibration is in a plane vibration. Now we have rocking vibration. Again, rocking vibration is again the in a plane vibration. Here you can see both the atoms are vibrating in the same plane. You can see it is in a clockwise direction as well as in an anti-clockwise direction. And but the important part is both these vibrations are in a plane vibrations. But if you compare these two with wagging, you can see both the atoms are coming towards us and simultaneously both the atoms are going far from us. Means they are not in a one plane. So that's why wagging vibration is out of plane vibration. So here you can see clear cut that both the atoms simultaneously are coming towards us. It means that there is disturbance of the plane, so atoms are not remain in the same plane. Similarly, twisting vibration is again the out of plane vibration. Here one atom is coming towards us and the other atom is going far from us. That's why again twisting vibration is out of plane vibration. And due to the all these six vibrations, the molecule get vibrate and the molecule.
All right, so this gives you a very good idea, but not all that information was useful to you. But the major parts of the information, not talking about the planes, I'm not talking about the further kinds of stretching or bending vibrations. All I am trying to talk about is that there are vibrations, which clearly give students the idea for the first time in life that light can affect each and every single organic molecule inside our body. And it actually depends upon the factor or strata or the portion of light from those electromagnetic spectrum, whether it's IR or UV or some other kind that can affect us. That's why some of those kinds are good for us. Some can take our, the images of our body, for example, X-rays, and some can affect simply that light can affect human body. So here we're talking about IR, and it clearly gives you the idea that the bonds do vibrate differently. They may stretch, they may bend, they may twist, and this happens when the natural frequency at which they vibrate and the frequency that we are throwing at them, irradiating at them, becomes equal. If that frequency is equal, it stimulates larger vibrations and energy is absorbed. This is known as the resonance frequency of that vibration. So now, since we have tested almost every other molecule, different organic molecule, we know what the resonance frequency vibrations of those molecules are, and that's what we are about to discuss over here. Now, each type of vibration would absorb characteristic wavelengths of infrared radiation. Now, if you remember a little bit of physics, you would understand that scientists express the reciprocals of wavelength in a unit called wave numbers. Now, I hope you already understand back from physics that wavelengths and wave numbers are reciprocal from one another. If wavelengths are measured in centimeter, the wave numbers are measured in centimeter inverse. I hope you have an idea about that already. Now, take a look at this. If you look at the x-axis of this graph, you would see the wave numbers in per centimeter units, and those that goes from 500 all the way up to 4,000. And 500 all the way to 4,000. On the right hand side, we have the y axis, which goes from top to bottom from 0 to 100, and there is percentage of absorbance. How much of that radiation is going to be absorbed? Now, remember, if it is absorbed too much, that means the same kind of resonance frequency has been absorbed, which means the closer it is to x axis. Can you hear me? Sorry, I had a little bit of an internet issue, so let's get back to it. I'm going to repeat a couple of my sentences just to make sure we are all on the same page. So I was talking about the graph and the x and the y-axis that we usually get after the iteration with IR. As you can see on the x-axis, we have the wave numbers in the same set units per centimeter. all the way from 500 to 4,000. And then on the right hand side, for y axis, from top to bottom, we have the absorbance in percentage from 0 to 100%. Now, the lower the graph curve goes, closer to the x-axis, the higher has been the percentage of absorbance of that IR, which means that we were closer to the frequency, or we exactly reached at the frequency which we have been calling the resonance frequency. They absorbed that energy because they were already vibrating at that energy. We irradiated them with the same energy, and then there was resonance because they stimulated larger vibrations. So the lower this curve is going to go in case of absorbance percentage, the closer to 100% it is, and higher is the chance that our molecule has that wavelength. But when we read these graphs, we need to define these graphs with proper terms. Just a minute. So I was saying that we need to read different graphs and we need to understand the certain graphs. This specific graph, as said in the caption below, actually belongs to the molecule ethylamine, the formula for which is CH3CH2 NH2, definitely NH2 being the amine group, as we studied back in chapter number 14. This gives the percentages. So we need to understand how, for different organic uh, so we can say homologous series or different formulae or different type of bonds, what it is going to absorb. So there we go. We have a huge table over here, table 18.3, which gives us the idea of the function groups, which contains specific bond, and the characteristic IR absorption range in wave numbers for those functional groups. Now we have CO for alcohols or esters, C double bond C, carbon-carbon double bond or carbon double bond oxygen or carbon triple bond nitrogen, CH, NH, OH. It gives us the idea which functional group do they belong to and what is going to be the range for it. Now, different functional groups have different ranges, and sometimes for a specific range, we may have two or three possibilities at the same time. Now, let me clarify myself. If I say C double bond C, that can be an aromatic compound containing benzene, or that can be an alkene having ending up in the same range for the wave numbers. Or carbon double bond oxygen is something that is present in amides, carbonyls, carboxylic acids, esters, all of them. And carbonyls and carboxylic acids, which means aldehydes, ketones, and carboxylic acids, which actually gives us a huge range of homologous series, are going to end up in the same portion. So how will we be able to clarify them with the help of these peaks that we are going to get? Wait a second. That's a little odd. Do the table that I am showing you and the table in front of your hard copies of the book the same? 18.3 I'm talking about.
Yes, it is.
All right, in previous book, we had a table with more explanation. This seems to be a little bit different. All right, let's go with this. But if this doesn't help, or the written portion doesn't help, I'm going to get you the old table because that is going to really help you with this. Okay, we can't be too specific when we are quoting the characteristic absorption frequency of a bond. The nature of the rest of the molecule sometimes shift the energy absorption in a particular area or a particular bond in a particular molecule. So, for example, we can say the amine group absorbs in the range of 3,300, 3,500 per centimeter. So, with different parts of the molecule, maybe the amine in ethylamine would be slightly different than methyl or propyl or some other aromatic amines, right? So the presence of the rest of the molecule may define the absorption frequency, and that may differentiate from one molecule to another. Now, we can use characteristic infrared spectrum of unknown compounds. We identify them by fingerprinting. Fingerprinting is a technique where we discuss an unknown compound, we take its spectra, and we match it with the database of unknown spectra. Fingerprinting is some technique that we studied back in the starting chapters, I guess, second or third chapter when we're discussing the spectra, NMR spectra. And fingerprinting is the same technique that we used back in IGCSE in the case of chromatography, where we discussed that we always compare the RF values of our chromatographies with the chromatographies performed by scientists under the same set of conditions. So just like the word fingerprint means that we usually have the fingerprint data of the entire world or a specific country with us, and whichever fingerprint that we get for any specific crime or for any specific purposes, we always run it and match it with the others to get a, a particular person that matches that fingerprint. So the word fingerprinting actually applies to the same technique, getting your answers and matching it with the whole set of database that we have to get a specific person or to identify a specific compound or a homologous series, maybe a functional group. It can be anything. Really, that goes beyond a lot of practices that we have. So the values needed to answer the question would usually be given to you as straightforwardly said in the book, so that won't be a problem. You see the absorption bands overlap considerably, so that's why we need to use a variety of techniques in cases such as NMR or infrared or mass spectrometry to work out the structure of a new organic compound. This we're going to study in A2. However, as well as their wave number bands, particular absorption have characteristic widths. Now, this is something that I was talking about that should be a part of the table. Since it's not the part of the table, so I will try and get a table that works out well for you. Now, the characteristic absorbances have characteristic widths. We can call them broad or we can call them sharp. Let me clarify what that word means. Take a look at this. This one is broad. Take a look at this. This one is sharp peak. That's the difference between the width of the peak. So sometimes the peak can be sharp. We usually represent it with an S, or sometimes it can be broad. We represent it with a B. All right. We may use other symbols for the representation. Now, moving on, the intensity can be strong or weak. Now, in case of a absorbance percentage graph, it can be closer to the x-axis, all right, or it can be farther from the x-axis. Take a look. If I extrapolate this, this is closer to x-axis. This one is something in mid. And if I talk about this peak in specific, this would be very less. So if I compare these three, this is the way we talk about our words strong and weak. So definitely I'm going to call this one as strong and this one as weak. In the case of absorbance, and I am saying it again and again for absorbance because there can be a transparent graph which is exactly opposite to absorbance. The whole graph is converted or moved upside down. So yeah, and then in that case, strong would be away from x-axis. In this case, the closer to x-axis means strong and farther means weak, and vice versa would be for the transparent graph. Since there are two kinds of graphs that we can discuss, how much is absorbed or how much is transferred and not absorbed. For example, the presence of hydrogen bonding makes the absorbance of OH bonds in alcohols and carboxylic acids broad. This is a very good idea that they have given. It's going to help you with the papers. If the peak is broad, that's probably because of hydrogen bonding. Now, the hydrogen bonding specifically tends to occur between OH, and that OH exists in alcohol's functional groups, and that also exists in our carboxylic acid functional group. Now, this may also happen to NH groups, and the NH can have a different presence in different functional groups. Maybe it's a part of amine. So this kind of discussion would be given to you so that you can talk about these answer questions in the exams. Now, by contrast, the CO bond in the carbonyl group has a strong peak, but at the same time sharp, not broad. All right. So this gives you an idea how OH bonds in alcohols and carboxylic acids differ from the width of as compared to C bonds in the carbonyl group, including aldehydes and ketones. Right. So we can talk about different tables, data, and different peaks. Since this table does not specifically talk about the sharp or the broad ones, this would be different. Now, since you don't have the table, explaining them won't make sense to you, so you specifically need a table. All right, give me just a minute so that I can make my point and I can explain to you how the difference in your current table is actually giving you a hard time understanding the point. Okay, now if you take a look at it, notice that this table actually discussed the type of bond, the functional groups they're in, the absorption range, and apart from that, strong or weak, sharp or broad, whether they are going to be broad or not broad. And they also tend to talk about the conjugation. Conjugation means that would there be a double bond uh, with single bond, and then there is a double bond. The word conjugated means double, then single, then double in a straight line. For example, that happens with dienes. For example, if you have CH2, double bond, then CH, then a single bond, CH, then a double bond, CH2. Now, this one is conjugation. One double bond, after the gap of a single bond comes again, a double bond, we call it conjugation. So it's going to be weak. We have this range for C double bond C, but this is going to be weak in case of simple alkanes. If they're conjugated, which usually happens in aromatic compounds, that may also happen to alkenes with di or trienes, it would be sharp, strong, sorry, my bad, strong. So it would be weak if it's not conjugated, and it would be strong if it is conjugated. All right. So this kind of helping words were there in the previous part of the book. I wonder why have they taken it out of it? Well, these kind of words give you a very good idea how to work with it. Now you can get these values. Of course, you can't memorize them, and nobody's asking you to memorize these. But if you get a table like this, you can obviously work out the unknown ones. Okay, let's work out an example. Okay, although it's written right over here that 18.9 is an infrared spectrum of ethanoic acid, now you do get a point that we have the C double bond O and then C single bond O and then OH in this portion. And of course, C bond C. So if you go back to the table, and I want to move back and forth, just a minute, to make my point. Now, if you look at this table, you would understand that if I talk about CH3COOH, the kind of bonds that we can discuss is one of them is OH bond, one of them is CO bond, one of them is C double O bond, and then there is the H bond. So there are different kinds of bonds that may all give us different values, right? I cannot actually go with this one, but I can try and talk about this one. Of course, we're talking about alkanes, and there we go for carboxylic acids. So you have different values for which you're going to get peaks. Some are going to be strong and broad, another strong peak, another strong peak. These are going to be a little bit closer to the x-axis, these peaks, and then one of them is going to be broad because of the presence of hydrogen bonding, which we previously discussed in the newer version of the book. So for this specific compounds, we may find three, four different values. I'm going to just talk about one or two out of these. So in between 1670 and 1740, they're going to be C double bond O peak, and in between 2500 to 3000, we're going to get an OH peak. Since I can't remember all of them, I'm going to talk about some specific ones. So let's move on and let's clear it up a little bit. So take a look. In between 2500 to 3000, and almost at 3000, you get a big broad peak for that OH. Of course, proving that it can be either a carboxylic acid or an alcohol. Now, A carboxylic acid would have a carbon double bond oxygen. Specifically, I picked the one that can differentiate for us. An alcohol would have CO bond, but a carboxylic acid would have C double bond O, which an alcohol misses. So I was talking about in between 1670 to 1740, somewhere like this. So over here we'll have 1670, and over here we'll have 1740. So there you go. All right. So you have this peak. And of course, this one is also sharp. Okay. So this gives you the idea what we are supposed to do. Are we good? I think that's